Hi all, good evening.
Uh, uh, until unless you have any doubt, please keep your mics muted. Sibi, thank you.
Hi all, can you hear me?
Yes, sir.
Okay,
Yeah, yes, sir.
okay, cool. Are we waiting for other guys to join?
Yeah, yes, sir. We can wait for 2 more minutes and then we can start.
Okay, cool.
Sir, I think you can start the session now.
Okay. I see a less attendance today. So, is there any specific reason? Like, have they dropped off or? Okay, anyways, so I'm sharing my screen. Do let me know like when you can see my screen. Is it visible?
Yes, sir, the screen is visible.
Okay. Thank you. Yeah, hi guys. Today is the second week of our the Statify Intro to Data Science, and in this week, last week, what we had covered is on the various nuances of what is data and how to do the various data transformation techniques and how to use the data when it is not available in the right format, how to convert categorical variable to continuous variables, how to evaluate the hypothesis of the samples which I had taken from the data, how to see like whether the samples are in the right way or not, right? So those are the various assumptions what we had done, and we had established the fact around how to use the data for good. Okay. So in this session, we will be covering about on the burning topic of machine learning and what are the various algorithms which are available in machine learning. So it will be a three-part session. So today is the session 1 by 3, wherein we'll be covering some of the algorithms from machine learning, which are the linear regression, logistic regression, and all those things. And in the second session, we'll be deep diving into some of the advanced machine learning algorithms, such as the random forest, decision tree, gradient boosted trees, how to fine tune my models, how to evaluate my model performances, and all those things. And in the third session, we'll be taking up a deep dive into the other paradigm of machine learning, which is the unsupervised algorithms, and how to use the unsupervised algorithms, wherein I will be dictating my model on unseen data. Okay. So without wasting much time, let's look into the agenda. So this is the agenda for today. So we'll be looking into what is machine learning and then the various types of machine learning which are available, supervised learning and the unsupervised learning, and then the key concepts around the supervised learning, the what are the features, what are the labels, what are the training data, and the unsupervised learning. And then we'll be going into the supervised learning techniques, which we'll be covering today. Okay. In that, we'll be covering linear regression, logistic regression, polynomial regression, and the various intricacies around linear regression, like what are the various cost function, how to minimize the loss, how to do regularization on top of it, and the other techniques around the support vector machine, the naive Bayes, which are the considered as somewhat different from the traditional machine learning concepts like the linear regression and the logistic regression. The other things what we will be covering today is how to evaluate my models, what I have built. So what are the various evaluation matrices for regression and what are the various evaluation matrices for classification? Okay. So what is machine learning? If I go by the normal Wikipedia definition, so this is what I had taken up from Wikipedia on what is machine learning. It says that it is a study of artificial intelligence concerned with the development and study of statistical algorithms that can learn from data and generalize to unseen data. So what we are trying to do is on a sample of data which we have with us, we are trying to make someone learn from it so that it can generalize to the unseen data which is there in the outside scenario. Okay. And thus perform tasks without any explicit instructions. Suppose say we are trying to make any say student or any kid who is there in your house, right? How to write A. Okay. We are initially trying to handhold the particular student or particular kid in the house to write how to write A. Okay. And how to write the alphabet B. So that we are explicitly saying that this is how you need to write. This is what are the alphabets. So that it can in itself, whenever it sees any of the unseen data or any of the real world applications, it can say that yes, by using A, B, and C, I can form this particular alphabets. I can do all these things. Whenever I see this kind of a pattern, this is A. Whenever I see this kind of a pattern, this is B. Okay. This is somewhat used mostly in the field of automation. It can build analytical models and can do automation, and it also can do large analysis on huge amount of data quickly and accurately. With that, we can build the predictive power within the model so that it can predict on unseen data based on historical data what we have. Okay. And the other thing is adaptability. So automation, efficiency, predictive power, and adaptability are the main concepts around machine learning. And also complex problem solving. Like it can be used to solve complex problems which might not be possible with human intelligence right now at this point of time. Okay. Let's see some of the real world applications of machine learning. To start with, let's look into healthcare. Okay, so in healthcare, what machine learning has been doing is disease prediction and diagnosis. Okay, and also personalized treatment, drug discovery. In the case of finance, like the fraud detection, algorithmic trading, credit scoring. Suppose say you have applied for a loan, you for anyone or any of you to get a loan, there are some of the other constraints that need to be satisfied. Suppose that you are not a credit defaulter. In the past, you have not defaulted. You are not a student. Getting a loan for a student versus someone who is settled is there is a thin line between those. So the banks try to prefer to give loans to those who are settled. So on those things like how to do the model, how to do like proper fraud validation, how to do the credit scoring for any of the individuals. In the case of retails, whatever you had seen, like in the case of Amazon or Flipkart, like in the cases of recommendations. Suppose say you are looking out for any of the product, you have such search for something, and given that the intelligence what they have, they can recommend you products to buy based on your past behavior and preferences. Suppose say you are a girl. For a girl, what are the different kind of a t-shirts or shirts can be recommended that would be different as compared to a boy. And also like based on your transaction pattern, based on your browsing pattern, the model can learn from those and can recommend back to you all those kind of uh, products which would be suitable for you right at this point of time. And the other thing is the pricing, like based on the pricing, suppose say I have got perishable goods, suppose say I have got tomatoes and potatoes in my inventory. I know that within a day my products are going to get spoiled. So how can I use my intelligence so that I can say that I can, if I reduce my price by say this much, then the products are highly likelihood of getting sold. Okay, so pricing strategies can be done on top of it. And similarly, the other cases are like marketing, transportation, the autonomous vehicles, what you see, like in the case of Tesla and all those things, route optimization, any of the courier companies, whatever, who are delivering product to you, they have got a strict pattern or map within them so that they are not randomly going to any of the places and delivering the goods. For them, the shortest time and the shortest distance is what they follow so that the time can be optimized and their fuel and the cost which they are bearing can be optimized for them. And the other things are like the predictive maintenances, entertainment, like the content recommendation, what you see in the Netflix, Prime Video, Hotstar, all those also have inherent machine learning models behind them, which run in the background based on your viewing history, based on your preferences, based on your like likelihood of listening to any music at any point of time in any point of the day. The inherent models can recommend back to you. Similarly, in the case of content creation, also like now with the advent of the Gen AI, you can see like people are also creating art, are also creating stories, also are also creating music using this basic or the complex machine learning models. Okay, so what is the baseline of any of the machine learning model? That is the data what we have. Okay, using the data we are building the machine learning models, and those machine learning models use those data to get feeded into it, and with those we are trying to build the modern applications which can be helpful for the mankind. Okay. So there are two types of machine learning. Just a second, give me 1 minute. Okay, I'm back. Can you hear me? Hello.
Yes, sir.
Yes,
Yeah.
sir, we can hear you.
Okay, yeah. So there are two types of machine learning. One is the supervised learning, the other is the unsupervised learning. Okay, so what do we do in supervised learning? In supervised learning, we provide direct supervision into the particular model that this is how you need to behave. This is what is my output, and this is what is expected out of you. Okay, that is the under direct supervision. We are trying to instruct our model that this is how the output need to be, or this is how you need to behave in particular scenario. In unsupervised learning, there is no particular supervision. There is no prediction as such that you want to perform in this way or this is the target. That is what is expected out of you. In place of that, we just leave the data as it is. So based on the patterns within the underlying data, based on the signatures within the underlying data, is my model trying to gain any signature out of it, or is my model that much efficient that it throws away all those information that yes, this is how your data is, this is what is the underlying history around it. Okay, So this is the definition of supervised learning. So supervised learning is a type of machine learning where the model is trained on labeled data. Okay, so keep always this like in your mind that for any of the supervised learning, we need to have the label data. Okay, and then the model learns to make predictions or decisions based on this label data, with the goal of being able to predict the labels for new or unseen data, right? So these are the some of the examples of supervised learning. So one of those examples is the classification, the other is the regression. So classification is identifying the category of an object. Example, see the spam detection in mails, the image recognition, where we are trying to classify X versus Y or A versus B, that this belongs to one class, that belongs to another class. Suppose say you want to distinguish, you want to build a model which tries to distinguish between two different types of cats which are there in the market, right? Or two different type of dogs which are there in the market, or two different type of vehicles which are there in the market. A model which is built which tries to distinguish between which is a bus versus which is a truck. So if you're trying to build anything which tries to classify into two different things, then that is called as classification. Okay. Whereas regression is nothing but where we are trying to predict a continuous value. So continuous value can be anything like stock market forecasting. So stock market is never like 0 or 1, right? In classification, it would always be 0 or 1 in case of a binary classification. Or in case of a multi-class classification, it can be say 1, 2, 3, 4, right? There are three different classes or four different classes which we are trying to predict using classification. Whereas in case of regression, it is a continuous value. So stock market, as you know, right? Stock market is a continuous value. The highs and the lows can be anything. It can be any number which is positive, which can be anything between 0 to infinity. And similarly, the house prices. Suppose say you are trying to buy a house. So what are the different price of a house? It can be say 1 lakh, 10 lakh, 20 lakh, right? So those are continuous values. So regression always goes with the continuous value, whereas classification always goes with the categorical value. So if I look into any particular data set, so this is what I mean by features. So whenever I would say these are, suppose I am trying to build the house price prediction, right? So the price of a particular house is say $1.29. Okay. So for a size of say 1100 square feet and it has got one bedrooms and one bathroom and the pin code is this, suppose it belongs to Bhubaneswar or say Delhi. For this, the price is this much. And so this is first row. And for second row, if I say the square foot is this much, beds are this, baths are this and this. So this is my another instance of the data. So each and every instance of the data collectively they form the rows of the data. Okay. And each of the target value which I have, that is the, in other words, those are called as labels, right? So we are trying to build a model on the label, and these are the features what I have for my particular model. And each and every this, as you can see, right, these are rows and these are columns. So columns collectively form the features and instances collectively form the rows of the data. And this is the target value, target, or it can also be said as label. Whereas in an unsupervised learning, what we do is there is no direct supervision. So we are trying to train on unlabeled data. So here, as you saw, right, there is a particular target for which we want to predict, build our model. That this is the particular price for which we want to predict that for so and so thing, this is what my price can be. But in an unsupervised learning, there is no such label within the data. In that, the model tries to identify patterns or structures or relationships within the data without any guidance. Okay. So these are some of the examples of unsupervised learning that have been used and that are used right now. One is the clustering. Okay. Suppose say this is how my data looks like, right? This is the x-axis, this is the y-axis. Over here, some of the data points are here and some of the data points are here and some of them are here. So if I don't give any direct label into the data, how my model would know that which data belongs to where? So based on the distance matrices, it tries to predict that all these blues are similar to each other and all these greens are similar to each other and all these oranges are similar to each other, because the distance between this and this is low, and this are low, and this all this data points are low as compared to the inter distance between these two clusters. Okay, so this is an unsupervised learning, and in this we are not providing that explicit labels that this belongs to class 1, this belongs to class 2, or this belongs to class 3. On its own, it tries to identify the pattern, and it's tries to build that particular model so that on unseen data, it can also build this particular kind of a clustering on its own. And the other things which like the applications are in customer segmentation, grouping similar documents. Like suppose say some customers are price savvy. Some customers are like who wants to buy when there is a price drop. Some customers are like who wants to buy in the weekend. Some are the other who want to buy in the weekdays. So in the case of customer segmentation, this kind of clustering algorithms are helpful. The other applications are in the dimensionality reduction. So dimensionality reduction is nothing but where we wants to reduce the number of features. Suppose say for house prediction, there are say what 4 features over here, right? Suppose say there are 1,000 different features. Suppose the size, beds, baths, zip, and then the other features like the city where it is, the locality where it is, the how what is the maximum temperature over that particular area, what is the minimum temperature of that particular area. Suppose say we have got 1 lakh features for a particular row, right? For a particular row, we have got 1 lakh particular features. So using a model on top of 1 lakh features can be difficult for us. So for that case, what we do is we go with this kind of a unsupervised learning, like the dimensionality reduction of PCA, finding the principal components of a particular thing. And the other is the TSNE, T-distributed stochastic neighbor embedding. So more on this unsupervised learning we will cover in the third session of the machine learning concepts. But for today, we will be covering on the supervised learning. Okay. So this is an example of how the supervised learning and unsupervised learning is. So in the supervised learning, we have got an explicit Y, which is the target. And in the unsupervised learning, we have got no target. So there is no Y over here. Okay. So based on all this access, all these features, we're trying to build a particular model. So supervised learning techniques. So as I mentioned, so we'll be covering on the linear regression, logistic regression, polynomial regression, SVM, and the naive Bayes. Okay. Let's go to linear regression first. So what is linear regression? So linear regression is a supervised learning algorithm used for predicting a continuous target variable. As I said, right? So regression is for continuous variables based on one or more input features. So we can have one input feature or multiple input features for a particular model. And the goal of linear regression is to find a linear relationship. As in the name of the linear regression, we are trying to find a linear relationship between the input variables and the output variables. Okay. So whatever my input is, based on that, I want to predict that there is a linear relationship within the input and the output. And the formula for any simple linear regression is, so there are two types of linear regression. One is a simple linear regression and the other is a multiple linear regression. Okay. So can anybody say me how to write what is a line of what is the equation of a line?
Sir, y is equals to mx plus c.
Okay. So let's write down that equation. So y is equal to mx plus c. Okay. So what is m and what is c? Can anybody tell me?
M is the slope of the line.
Okay. And c is?
C is the intercept.
Okay. So as you guys, you might have learned it before also. So we can represent a line in the form of a particular equation that y equal to mx plus c. Okay. So suppose say this is the x-axis and this is the y-axis. Okay. For any of the line, I can write it as, suppose say it starts from 0 and it goes like this, right? So there is a linear relationship between y and x. So here the c is 0. That means when c is 0, y is equal to mx, okay? Where m is the slope between the slope of the line. That means y2 minus y1 by x2 minus x1. This is the slope of the particular line, right? So when c is 0, that means we are assuming that there is no intercept for that particular line, okay? And y is directly proportional to x. So as x increases, y is also increasing. So there is a linear relationship between the input variable and the output variable, okay? So there is a direct relationship between the y and the x. And the direct relationship can be established by m. M is nothing but the slope of the particular line, okay? So it can also happen that there can be some intercept within the particular line as well. Suppose say it has a particular bias within the data, and this is C, okay? And my line goes like this, okay? Similar to this, the slope is still M. Slope is still M in the same angle it follows, the tan H is the same. And but there is a significant bump within the data. When X is 0, Y is not equal to 0. Y is equal to C, okay? So this can be represented by Y equal to MX plus C. So the same thing what we are trying to do is in the case of a linear regression. In linear regression, we are trying to establish the fact that as x increases, y is also increasing. We are saying that there is a direct relationship between the x and the y. Okay. So let me clear this. So for a simple linear regression, we can write that as y equal to beta naught plus beta 1x plus epsilon. Okay. So where y is the target variable and beta naught is the intercept. So C, what we were writing for a linear equation is nothing but beta naught, okay? And beta 1, beta 2, beta n are the coefficients for each feature. Okay, suppose this is a simple linear regression. That means we are assuming that there is only one x-axis and there is only one x variable. So beta naught plus beta 1x, okay? And epsilon is nothing but the error term or the residual. So epsilon, how we can get? Epsilon is the noise within the particular data. Okay. Epsilon is what? Y minus beta 1 x, assuming beta not to be 0. Okay. Minus beta naught. So this is the error term. So error term is nothing but suppose we are trying to, this is my y and this is my x. And this is the particular line what we have establish that this is how the relationship would be between y and x. So anything which is coming between this particular line and the x is denoted by epsilon. Okay. The difference between the slope and the particular data point is denoted by epsilon. Okay. So in case of multiple linear regression, suppose we have got multiple x variables. So this is a simple linear regression. It can be represented by 2D. Suppose we have got multiple x's in my particular data, then how can I build a particular this thing? So for simple linear regression for a 2D, this is a line. So can anybody say me like for if I have got multiple variables, what would what it would be? Will this be a line or what?
It will be a surface.
Yeah, so it would be a surface, or in other words, it would be a plane. Okay. So a plane which is cutting across multiple different axes. Suppose this is one axis, this is one axis, right? Assuming that we have got a individual lines for each, right? We can't have multiple lines for that, right? So if I club all of these lines and aggregate that into a single form, it would be a plane or a surface cutting across the having a common slope, right? Having a common slope and a common intercept. So that is how we can write for a multiple linear regression. So for a multiple linear regression, these are the terms. So epsilon would be the same thing, and beta naught in place of beta 1x, there are multiple. So multiple coefficients for multiple different variables what I have. So this is what is in the same thing what I was saying. So this is the x-axis, this is the y-axis, and this is the all the data points what I have, right? So suppose that this is 1, this is 2 in my x-axis, right? This is 3, this is 4, right? So when x is 1, y is suppose it is 1, and this is 2. So based on that, all those things I'm trying to find a particular line which will be cutting across the all the data points that I have, so that my error term which I am getting, the random error epsilon which I am getting, is minimum. Okay, is that clear for all? The error term which I am getting, it should be minimum. Let me I use the other thing. So this is the error, okay, and this is lying on the particular line. So this is epsilon 1, okay, this is epsilon 2, say suppose epsilon 3, and this is epsilon 4, this is epsilon 5, and this is epsilon 6. So what is my, this is all the epsilons. If I do a sum of all the epsilons and take an average out of it, then that needs to be minimum. Okay, that means this should be tending to 0. Okay, that error term should be tending to 0. So how can I fit a line so that it would be going through all the data points, like near to the data point, so that the error term which I'd be getting between the data point and the particular slope would be minimum. That means it should be tending to 0. To tackle around that, what I have is the mean square error. Okay, so the mean square error is nothing but, so y cap is the target variable, okay, and y is my original truth that I have. Okay, so this is what my model is predicting, and this is what the original data is. So what I'm trying to do is I'm trying to minimize the prediction versus the actual. Okay, for all the data points. Suppose I have got n data points. So for all the data points, what I'm trying to do is I'm trying to take the difference of this and do a square of all the differences and take an average out of it. That's why it is called as a mean squared error. It is a squared loss, right? The square of this. So can anybody else tell me? So can if I can build up any other cost function for this, why can't I take only yi
Mean
minus?
absolute error.
Yeah, so why can't I take only yi minus yi cap?
It will cancel the positive differences and the negative differences.
Okay, okay, okay. So who was this?
Swayam Jha, sir.
Yeah, so as Swam was mentioning, so it will cancel all the positive and the negative differences. Okay, so what do you mean by positive and the negative differences? Okay, so see here, this, if I take the difference of this minus this, suppose that this is my target variable, right? So this is what I'm predicting for me. So this is the target variable, this is the predictive variable. So the difference between this and this point, suppose that this is coming as say 3 and this is coming as 4. Okay, and so this is coming as say 2 and this is coming as what, so this is coming as 2 and this is coming as say 1.5. So above the line, if I take the difference, it would always be positive, right? If I take the difference of this line and this, it would always be negative. So this is always positive and this is always negative, right? Suppose say I have got a line in which the data points are equally distributed over here, right? So suppose that this is coming as 1 and this is coming as -1. Okay, so this is coming as 2 and this is coming as -2. Okay, if I take the difference between the target variable and the predicted variable and do a sum of all of that, sum of yi, y minus yi cap, right? It would cancel out. So what? So the difference is y minus yi cap. is for the first is 1, and for the second is -1, and for the third is 2, and the other is -2, right? So it would come as 0 for me. So in this case, whatever I will be getting would not be the optimal for me for this case, because it is cancelling out the positive and the negative. It is not giving a clear, distinct picture that how well is my line, the one which I am trying to fit on the target variables. So to tackle around that, what we can do is we can take an absolute value of it, right? Will this solve? Can anybody say me, will this solve this particular issue? Hello, am I audible?
Yes, sir, your
Hello.
voice is completely clear.
Yeah. So can anybody say me, if I take an absolute of this, so will this solve? Like, it would always be positive. So 1 plus 1 and plus 2 and plus 2. It would be what? 2 plus 2, 4, 5, 6. So the total error would be coming as 6 in place of 0. Okay. So this would also solve the particular problem, that if I take an absolute value of it, as somebody Swam was saying, that it would not cancel my positive and negative. So by taking an absolute, it will solve a particular issue, right? But taking an absolute would unnecessarily, like, for say, suppose say I have got 1 lakh data points, the value would be an order of n times as my data points are. Suppose I have got 1 lakh data points, so the value would be in order of that many data points which I have. Suppose 1 lakh, so it can be, even if the difference between the predicted and the target is 1, right? It would be, the error term would be 1 lakh, which might not give a detailed picture out of that how much is the difference between my target and the predicted. So one way to solve is, if I divide my values by the total number of samples that I have, right? 1 lakh by n. So 1 lakh by 1 lakh, it would be 1. So on an average, my difference between my target variable and the predicted variable is 1. So what I'd be trying to do is, I will try to find that the difference is not that much. It is only 1. Okay, so this is nothing but the mean absolute error. Okay, this is an absolute difference what we're taking, right? So it is an absolute error. And if I take a mean out of it, it is called as a mean absolute error. Okay. And the other errors which I can do is the mean square error. So suppose I have got more of the data points and the losses are of higher magnitude, then what I can do is, I can take a difference of that and take a square of it. So if I do the square of it, it would tackle my this thing also, like the square of a negative is positive. So it would solve the particular issue, like solving for a this negative and positive cancellation. And also, like, a square of any uh, large difference what I have is also a large number. So in that way, we can also target for the any of the large differences. Suppose say I have fixed this particular line for me. Okay. I hope everybody is in sync with me what I'm trying to understand. Right. Suppose these are the target variables and this is the predicted value what I have done. Right. And this is another data point which I have, which is far more than the target line, right? Clearly, this is an outlier for me. And this point would be having a large error coefficient for me, right? Suppose this is 1, 1, 1, 1. So 1 square, sum of 1 square plus this large error. Suppose this is some 1 lakh, right? Or say 10,000 or say 1,000. So this 1,000 square I'll be taking up, so that I'll be also penalizing for the large errors which are also there. So for that, what I do is I take the mean square error. And the other thing is the sum of square error. So see, in the sum of square error, we are not taking the absolute, we are not taking the dividing it with the number of samples what I have. We are just taking the square differences between the error. So it is the sum of square error. Okay. And the other thing is, I have fixed this particular thing, right? Y equal to beta naught plus beta 1 x plus epsilon. So what should be my beta naught and beta 1 so that I can find this optimal line for me? Okay. How can I estimate the beta naught and the beta 1 for my particular model so that I can find the optimum line which passes through the data points or the near to the data point so that my error is minimum. Okay. So there are various ways in which I can estimate my beta for my linear regression. So one of the commonly used method is the ordinary least square method or the OLS. Okay. So this is the most common question which is asked in the interviews and the most common thing what any of the people who is preparing for any data science interview need to know, that for solving for any linear regression we can either go with the ordinary least square or there are other approaches as well. So what we are trying to do in the ordinary least square for this thing, for the sum of squared errors, how can I write this? So this is yi minus what was yi cap is beta naught, or in other words I can say that if this is a matrix, beta into x, right? Okay, beta cap into x. Okay, so what I'm trying to do for the sum of squared errors, yi minus beta cap I and x I, I'm trying to minimize this. Okay, and what is my target? Can anybody say me like what should be my target? Should my sum of square error be high or sum of square error should be low? Hello.
Yes, sir.
Yeah, so what should be my sum of square error? Will this be high or which it should be low in ideal conditions? What I'm trying to minimize, I'm trying to minimize the sum of square errors, right? So for that, I want my sum of square error to be near to zero, or it should be equal to zero. Okay. So if I make this equal to zero, so what I'm saying is yi is equal to beta I cap xi. Okay. This is what I'm trying to prove. And beta I cap, then I have to minimize that in such a way so that I can find my optimum beta matrix, which should be making the sum of square error equal to zero. Okay, so if I solve that particular equation, then it would come in this particular way, that beta cap is equal to x transpose x whole inverse into x transpose of y. Okay, so it's just coming in this same way, that beta cap is what? yi into x inverse, right? Xi inverse. If I write the Xi inverse in the other way around, it would be this way, right? X transpose X inverse into X transpose into Y. So beta cap would be this much if I solve by ordinary least square, where Y cap is equal to X into beta. Okay. So beta is nothing but the ordinary least square estimator, X is the matrix, and T is the transpose, and these are all the things that you know. Okay. Other than that, I can also solve that by gradient descent method. Okay, so this is ordinary least square method and this is the gradient descent method. So I think gradient descent you guys might have studied in your 11th and 12th and also like in your uh, uh, bachelor's also, that for any of the loss minimization. So beta, what I'm trying to do is I will be updating beta based on the loss what I have. So the loss function is this, right? The mean squared error, if you see the function, right? So this is nothing but h beta xi is nothing but y cap, right? yi cap, and this is yi. Okay, for this particular loss function where m is the number of samples that I have. You guys remember, right? This is the mean square error what I have. So for this particular mean square error, this is the particular cost function. And for this particular cost function, I am trying to differentiate the cost function with respect to beta so that I can find out which is the beta so that my total loss function would be near to zero or is equal to zero. So here we have a different term which is called as alpha. Alpha is the learning rate, which says that how fast would be my loss function going to converge. If I have a large alpha, then the rate of convergence would be highest. If I have a small alpha, then the rate of convergence would be quite low. It would be diminishing at a quite smaller rate, but in that case, we will not be losing out on the local minima. Okay. We'll be not getting stuck in the local minima. We'll be going towards the global minima as a whole. So for any of the ordinary least square technique, to achieve this particular method where beta is equal to x transpose x inverse x transpose y, for this, the assumption is that my data needs to be linear. So the there is another thing called as blue. Let me write that in blue only. Best linear unbiased estimator. Okay. So this is a thing which has been coined by statisticians, which follows the Gauss-Markov theorem, that for any of the estimator, that means for beta, for to be a good estimator, it needs to be blue. Okay, where B is the best, L is the linear because it's a linear model, and U is unbiased. It needs to be unbiased and unbiased estimator. So it needs to be blue. So for that, there are various assumptions which we need to follow. That means for any of the linear regression, the target between the independent variables and the output variables need to be linear. Okay. That means for any of the y and the x, right, it needs to be a linear graph. Okay. It needs to be a linear graph. It cannot be an non-linear graph or like this or like this. Got it, right? So it cannot be any non-linear relationship should not be there between the y and x. If there is a non-linear relationship, we cannot use the linear regression. So as x is increasing, y should also increase. It should not be the other way around. As x is increasing, y is decreasing. So it cannot be like this kind of a graph. It always needs to be linear graph. And the other is the independence. Hello.
Yes, sir.
Yeah, I think my screen, like the sharing was stopped. Okay. Can you guys see my screen?
Yes, sir.
Yes, sir.
Yes, sir.
So the other thing what we need to assume is, let me note everything down. So first is the linearity. That means there is a linear relationship between the input and the target variable, x and the y. And the other is the independence. That means the residuals or the errors are independent. That means there is no correlation between the residuals. Okay. For that, what we mean is for any of the model what we are trying to build. So this is y and this is x, right? Suppose this is the line what I had fit, and this is the set of data points that I have. Any of the errors which I'm getting, so this is an error, right? This is an error and this is an error. This is an error. The difference between the line and the data point is an error. Okay, so this is an epsilon which is error. Okay, epsilon 1, 2, and dot dot dot. Those are the errors. So by residuals, what I mean is the errors. Okay, the residuals are independent of each other. That means this residual and this residual is not correlated to each other. That means if this residual is increasing, it should not happen that this residual is also increasing. Okay, that is, there should be no correlation between the residuals. Okay, this is on the residuals what I'm talking. So first thing is on the linear relationship. So the linear relationship should be there within this data points, those blue data points what you are seeing, right? And between the, sorry, between the residuals what I'm talking, between the yellow, sorry, the red thing what you are saying, this residual should not be correlated to each other. Okay. And the other thing is homoscedasticity. So this is also on the residual. Okay. So on the residual, what it needs to be is it needs to be independent and it also needs to be homoscedasticity. That
Sir,
means, yeah.
could you explain the second point again, like the independence? What is the mathematical, like how can we mathematical show that the residuals are independent of each other?
Yeah,
Like
so I'll
they
be
don't
showing
have
you.
correlation.
Yeah, I have got like code also. I'll be giving you code walkthrough. In that, I'll be also plotting for some of the sample data. And in that, I will be also telling you like how to test for independence, how to test for linearity, how to test for everything. Okay.
Okay,
So just have
okay.
patience and I'll be covering you everything. So the other thing is the homoscedasticity. That means the residual should have a constant variance at every level of the independent variable. Okay. That means the variance, if I try to plot all these residuals, that means they should not be too much distributed. That means the variance between them should not be too much. That means the variance between the error terms need to be constant at all point of time. And the other is normality. And for the residuals, so for residuals, it needs to be independent. For residuals, it need to have a constant variance. If it doesn't have a constant variance, then it is called as a heteroscedasticity. Okay. And the other thing is normality. So the residuals should be following a normal distribution. If I plot all the residuals, then my assumption is it would follow a normal distribution. And the other thing is on the data points, first I said that they need to be linear. The other is they should not be multicollinear. That means the data points should not be correlated to each other. That means suppose I have got the price prediction, right? The home price prediction thing. I should know that the features, that means the square foot of the building or the house and the other features, suppose say the age of the house, right? They should not be related to each other. If those are correlated to each other, then it is difficult for a linear regression to fit and also to estimate the parameter which is blue, which is biased linear, best linear, unbiased estimator. Otherwise, it would not be unbiased in that case. And the other thing is like there should not be autocorrelation within the data. That means the data points what I am used. So keep in mind, so there is something called as autocollinearity and multicollinearity. So autocollinearity is nothing but within the same data point. That means the square foot, all those instances what I have for the data, they should not be auto-correlated to each other. That means all of the data points, suppose say the instance at row number 1 and row number 1000, they should not be auto-correlated to each other. That means the features are independent in itself as well. Okay. So these are the various assumptions one needs to remember and always like this is also one of the common question like whenever you give for any data science position, all those things are quite commonly asked. The other thing is that the regularization. Okay. So regularization and regression. Suppose I have built this particular model. I have built this particular model where it is y and this is x. Okay. And this is the graph. This is the line which is coming for my this thing. And all of these are my data what I have, right? And this is the perfect line which is there for me. And this is passing through the data points and the errors are also quite less. Okay. But this is what like the model which I am building is on a sample of data, or in other words, the sample data is known as the training data for my model. Based on the training data, I have fit this particular model and it is performing quite well. So the error term which is there is say is coming as 0.05 for me. Okay. While I have fit the particular model. So I'm quite excited and I'm quite sure that this model is the best model that I have built and this is the best in the market which is there right now. But in the real world scenario, when I'm trying to use this particular model using the set of parameters, right, the beta of my model, I'm trying to estimate on an unknown data point which is there. So in that case, what I'm seeing is my error is coming more than 0.05. Suppose it is coming as 100. Okay. That means my model is unable to generalize well for any of the data points. Suppose this is another testing data. So these are the testing data. And for this, it is unable to predict. In real world scenario, it should have been like this. But given that my training data is like this, it is it has predicted a line like this. So my model which I have built is not generalized to the unknown data. So in other words, what I could say that my model has overfitted, right? It has overfitted on my existing data, what I have. So overfitting is quite a concern in case of machine learning models. That means I don't want my model to be stricter in terms of the data points that I have taken or considered. It should be generalistic. It should be generalized in such a way so that it can also be well suited for unknown parameters, for unknown data points as well. Suppose I have got a lot of noise in my data. So noise can also be crucial, play a crucial factor for my model to overfit. So to tackle around that, there are many techniques which are available through which I can overcome this particular overfitting thing. Okay. One thing is in the case of linear regression, what we do is the L1 regularization, or the other is the L2 regularization. Okay. In L1 regularization, what we do is we add a penalty which is equal to the absolute value of the magnitude of the coefficients of the loss function. Okay. So whatever loss function what we have in case of linear regression. So this was my original loss function that I had, right? This was the mean square error or the sum of square error. Okay. Yi minus sum of this yi cap. Along with that, I'm taking the absolute sum of the coefficients along with the multiplying factor, which is called as lambda. Okay. So this is known as L1 regulation. The concept behind this is I am adding an extra term so that it can go to exactly zero after effective performing the feature selection technique, so that all those features which are not that much important to me and the coefficient value which is coming for me after doing this L1 regularization, those can diminish and go to exactly to zero, so that those features which were like making my model go overfit on the training data, I am removing those features from my model. Suppose say in the house prediction thing, suppose say I have got the square foot thing and the age of the house, right? So the beta for the age of the house, suppose say beta 2 was mostly influencing my model to overfit. So what I have done is I have added an extra term over here, and when I am trying to minimize this loss, I will get that beta 2 is near to zero, so that the influence of the beta 2 is removed from the model, and through that way I'm not using that particular feature in my model building. Okay, the other is the L2 regulation, which is the ridge regulation. In place of an absolute loss, what I'm trying to do is I'll take the uh, squared
Sir,
term with L2 now. Yeah.
sir, could you explain again how L1 regularization helps in feature selection?
Yeah.
Hello.
So yeah. So as I was giving the example, right? Suppose say for my model, there is beta 1, beta 2, and beta naught. These are three terms which are there in my model, right? Beta naught plus beta 1 x1 plus beta 2 x2, right? Y is equal to this line equation what I have got. And after doing my model, this is giving me this kind of a graph. Okay. So what I'm trying to do is I have added another extra term in my cost function. That is the absolute value of all the betas. So W, in other word, suppose this is beta. Okay. Beta j. What I'm trying to do is adding an extra term beta j, so that it is an absolute sum of all the betas that I have in my particular cost function. So this would be beta 1, beta naught plus beta 1 plus beta 2. Okay, so in the cost function, I'm adding that in such a way that whenever I'm trying to minimize the loss. So while I'm trying to minimize the loss, suppose by doing the gradient descent, okay, differentiation of this cost by beta, right? I'm trying to minimize that particular loss. And in that way, I'm trying to say that my loss needs to be minimum. And in that term, I am adding another extra term so that the difference of this would also get minimized at that point of time. And that would have also a crucial role while I'm estimating the particular beta j. Suppose say while I'm estimating the beta 2, right? Beta 2 is equal to beta 2 minus alpha of difference of the loss function, this loss function by beta 2. While I'm trying to do that, this would go to 0 because it was hampering my cost function what I had, right? So through that way, we are trying to minimize this particular cost function. And the other way to do that is through the L2 regulation, where in place of an absolute value, I'm taking the squared loss or the squared value. Sorry. Hope this is clear for you.
Yes, sir.
Yeah. So I think so today's session would be taking a good amount of time. Like we have a lot of concepts to cover and a lot of things which you have planned for today. So let me give you an example of how linear regression is done in daily life and how you can do that in Python also. Okay. My screen is visible, right?
Yes, sir. It is
Yes,
visible.
sir.
So let's perform the linear regression. Okay. So for linear regression, what how I can do is I can use the available libraries which I have. So one is the sklearn, which is the scikit-learn. So from scikit-learn, there is linear model. So under linear model, there is linear regression. So from sklearn, I have imported the linear regression, and I will come to this matrix later, which is the mean squared error and the R2 score. We will come to this later. But for now, we will be using this on how to test that. So I have, suppose this is my X, which is there, which is my independent feature, and Y is my target. Okay. So this is what I have built. So this is for every X, this is the corresponding Y. Okay. So when it is 7.49, this is 6.33. When it is 1.90, this is Y is 9.40. So based on this Y's and X's, I'm trying to predict for unseen data what can be my target would be. Okay. So for that, I am splitting my data into two parts. One is the training data and the other is the testing data. Okay. Training data is nothing but my input data to the model. That means I want to say how good my how to train my model on that. And on the test data, I'm trying to predict my model and just to test like how good my model is. So how I'm splitting? I'm splitting it by 20%. So 80% of the data would be in training and 20% of the data would be in testing. Okay, so this random state is 42. So this you can take as any number. So this is like whenever I'm trying to do any kind of repeated exercise. So because I'm doing random split of the data, this needs to be equal every time. And from the scikit-learn, I have already imported linear regression. So the model is linear regression. And then I'm going to do the model.fit xtrain and the ytrain, where xtrain, if you would see, this is the xtrain. So sorry, that was some other. So this is my xtrain, right? And this would be my ytrain. Okay. So this consists of the 80% of the data that I have, and on that I'm trying to fit the particular model.fit xtrain ytrain, and then I'm trying to predict that for all the unseen data, that is the X test, what is my X Y braid. Okay. So based on that, I'm getting a mean squared error of 0.65 and an R score of 0.80. Okay. So more on this like mean squared error and so mean squared error, right, as you had seen from the equation. So that is the difference between the Y target and the y predicted. That is y test and y pred. So the square difference between this is nothing but the mean square error. So mean square error is coming as 0.65. Suppose say I have got my samples, right? So these are the x's. So suppose say my x is 1, 2, and 3. So for each of this, what would be my y's? So when x is 1, if I try to build this, or say 10, 20, and 300, right? So for this, there is a linear relationship between the x and the y. So when x is 10, y is 32, 20, 60, similarly 300, 843. And I can plot the results as well. So if I plot this, so this is the line which I am getting. Okay, the red line, what you see is the line which I have predicted using my linear regression model. Okay, so these are the actual x's that I have, and this is the y value. Okay, and my objective was to minimize this x and the y, x and the particular line. And how I can check the various assumptions which I have made for my data. If you remember the linearity, independence of residuals, homoscedasticity, right? Normality of residuals, QQ plot, right? So suppose if I do a scatter plot on my data. So this is the scatter plot on all the X and the Y. So here what you have seen is on the uh, test data. So this was the test data and this is the line what I have, and this is predicted line what I have. And suppose if I do the plot on all the data points that I have, I can see that there is a linear relationship between the x and the y. Okay, as x is increasing, y is also increasing. So this is a linear line which I have fitted on the particular this thing, which says that there is a linear relationship between x and y. And the other is the independence of residuals. So for all the residuals or the errors that I have between this y, between this line and the particular data point, using all those data points, if I plot that and I see that, then I see that there is a independence between the residuals. Okay. And similarly, the homoscedasticity check, which says that there should not be any, the variance need to be constant. So if I plot that, then I see that on an average, the variance is almost constant for the particular, all the residuals. And the other assumption was that the residuals need to follow a normal distribution. So if I plot all those residuals, find out the mean and the standard deviation, then it almost follows a normal distribution, even if that is somewhat left skewed, but still it follows a normal distribution. And the other is the QQ plot, wherein I am seeing the uh, for the residuals, if those are autocorrelated, if those are like correlated to each other. So for that, I am doing the QQ plot. Okay. Let's do the same thing on a sample data set. Suppose I have made this particular data set wherein this is a particular data frame for a students, right? So for the students, this is the exam score which they are getting, right? For suppose say the student whose ID is 0 or student whose ID is 1, this is the number of hours he or she has studied, the attendance which he or she had got, the number of assignments they had completed, and the gender of the particular student. Okay. Based on all these things, I'm trying to predict how much exam score the particular student would get. Okay. So for that, what I'm trying to do is, given that this is a categorical variable, right? Gender is a categorical variable. And as you know, like we need to have the continuous variables for the linear regression. So first thing first, we need to convert this categorical variables to continuous value. So one thing how I can do is, I can do that as a one-hot encoding. If you remember the day one session, in that what we have done is we have converted those into one-hot encoded values. That means where it is male, it can be 1 and female is 0. And then I'm doing the train test split and using the exam score as my target variable and using the particular model. So if you remember there, we had used the linear regression from scikit-learn. So this some of the other functionalities like the hypothesis testing and all are not available in the scikit-learn. So what we have used is the stats model API. Okay. So stats model has got the other features through which you can do the hypothesis testing and also the other tests which are there or needed for my assumptions check. So I have fitted this particular model, and based on that, this output are coming. Okay, so this is the extend, widen, and all those things. And on this, I have fitted the model, and this is the model summary. Okay, so here are some of the things like the R square is coming this much, adjusted R square is coming this much, and number of observations are 80. Okay, and the number of residuals, degree of freedom of the residuals, degree of freedom of the model. Okay, EIC, BIC score. So like there are many different information criteria that need to be checked. But for you, I don't want you to deep dive into all those things. Just for now, what we can see is there is something called as a p-value, which we are getting for each of the particular values, each of the particular features that I have. So constant is nothing but the beta naught. Okay, beta naught corresponding to the particular model, and the hours studied. Suppose say this is the x1. Okay, so beta 1 coefficient. So beta 1 coefficient is coming as 0.05. Beta naught is coming as 49.84. Beta 2 is coming 0.3, and this is how the betas are coming for my particular model. Okay, and for each of the features, what I'm trying to do is a hypothesis test that those features are not directly impacting my they have got a constant uh, that is they have got a direct influence on my model behavior. Okay, for that I'm trying to do a t-test on the data, and on that I'm trying to get the p-values for the particular this thing. So if I do the hypothesis test on the data, what I'm looking is if the p-value is less than 0.05, then I consider that the null hypothesis is significant and I can use that particular feature. Okay, so for this, the p-values for the constant, our study attendance and all this, these are the p-values what I'm getting. Okay, and from that what I got to know was for the constant it is less than 0.05, and for attendance it is less than 0.05, because 0.05 was my confidence interval which I had taken. So because it is coming as less than that, so I can use this constant and the attendance for my model and discard the other features from the model building, and can go ahead, and by these two features only I can say that what would be my output score, model score. Sorry, not the model score, the exam score for a particular student. Okay, that means the constant and the what was the other one? It was the uh, attendance. So using attendance and the this and the constant value. So our studied and assignment score and the gender, they are not directly influencing my exam score. Only the attendance and the constant value is impacting my exam score. With this only I can build my particular model, and that would give my corresponding output. Okay. And so this is the other thing what I can plot, like this is the actuals versus the predicted graph. And the tests, what I can do is the linearity check. Okay, so for linearity check, someone was asking how I can test that. So by by visually, I can say that if there is a linear relationship between the output and the input. Okay, and for the independence of the residuals, for the residuals independence check. So if you remember in our this thing we had, right? So for linearity check, I can do a visual plot and I can get an understanding from that. From the independence check, where I want to see that there is no direct correlation within the residuals. So for that, the test what I do is the Durbin-Watson test. Okay, so these are the different like statistical tests which have been developed and available for you. You can use those directly from Python, and that would give you a particular value, that the score value. Okay, using the score value and using the p-value for each of the particular tests, if it is less than 0.05, then I could say that those are statistically significant. That means my null hypothesis is null hypothesis is true, and the particular test that I'm trying to do, suppose say I'm trying to do the homoscedasticity check. or the normality of residual check. That is true, and I can go ahead and use my particular model. If that is not true, then I have to do any other transformation on the data or use any other external data, or the particular linear regression which I'm trying to build is not correct. Then I have to go with any other models for my particular task. Okay.
Sir, for Durbin Watson statistic also we need to follow the 0.05 rule. Like, what should be the value of the DW stat?
That I need to check. Like, I'm not also sure on this, but for other tests, it follows a statistical, like the either
Yes,
a
it's
t
big
test or
value.
a z test. Sorry.
So, no, for the other for the other test, I think so. It just corresponds to the p-value, right?
Mm-hmm.
But for this one, we need to like, what's the range in which, if it falls, then we can say that our hypothesis is true.
Okay, I'll check for that and I'll give the range for this, like what should be the ideal range for the Durbin-Watson test. Okay,
Okay, sir.
I'll let you guys know on that.
Okay, sir. Thank you.
Okay. Okay, so coming to the other thing, so this was on the linear regression. Okay, so has anybody got any doubt on linear regression? We can look on that before moving into the other aspects of other model. Anybody like who has got any of the slightest doubt can ask me.
If anyone is having any doubt, they can raise their hands.
I know there, like, it was a lot of concepts I had covered, and it might have also, like, uh, some of you might be reading it for the first time, some of you might be looking it for the multiple times also. So at the end of the session, like, I'll be providing all the slides and all, so you can go through them. If you have got any doubt, do let the team know. Like, they can forward all those doubts to me, and I will be uh, like happy to answer them as well. Okay. So coming to the next thing of regression, the logistic regression. So in linear regression, what we have done is we were trying to predict a continuous variable. That means, for suppose say the example of the stock market, right? Or the house price prediction, wherein it was a continuous value. It can range between anything 0 to 1 or negative value, right? It can be anything. In that case, we were trying to build a linear regression out of it. Whereas if you want to build a classifier out of it, that means if the target value is either a 0 or 1, that means it can either be 1 or 0 or yes or no, or it can be continuous or it can be categorical, like it 1, 2, 3, 4. Okay. In that case, we can build a classifier out of it. So in logistic regression, what we do is we are trying to build for the cases where it follows a categorical output. That is, either it can be true or false. So the concept around that is, if you're trying to build that, then the output of the model should also be either 0 or 1. Suppose say I have built a linear regression, right? Where in this case, it can be anything that is there in the x-axis and the y-axis, right? It is directly proportional and it varies as my x increases and the y increases. So how to use all those x values so that I can fix my y to a certain range, such that I can say that if it crosses the threshold, then it is 1. If it is below the threshold, sorry, it is 0. Okay. What should be my threshold so that I can say that if my model is behaving in such a way, if it is crosses the threshold, I would say that 1. If it is below the threshold, it is 0. Or what should be the plane? Can the plane be like this, or can the plane be like this, or the plane be like this? How the plane should be so that I can differentiate between the inputs and can predict my output accordingly. Okay. So for that, what we have is a logistic function or a sigmoid function. Okay. So sigmoid function is nothing but it follows this kind of a graph in S sub graph, which says that based on this value, so 1 by 1 plus e to the power minus x, if I input my x values for anything x that I have, it can give a corresponding value which is between 1 to 0. Okay, so this always go from 0 to 1. Okay, and the middle point of this is 0.5. So if I take this as the threshold, anything which is more than 0.5 can be 1, or anything more, less than 0.5 can be 0. So this is, in other words, the sigmoid function, what you see. So this is my cost function for my, not the cost function. So this is what is my equation for my logistic regression. Okay. So for the linear regression, if you remember, right? So there what we had, it was y is equal to beta naught plus beta 1 x plus c, right? Beta naught plus beta 1 x plus c, right? If I want to do the same thing for a logistic regression, so here the y is not this, but the y is a function of this. Okay, y is a function of this, so that I can say that based on my values, it can either be, output can either be 0 or 1. Okay, so this is the formula for the logistic regression, which is in the same as you see for the linear regression, where z is equal to beta naught plus beta 1 x plus. It has got a linear combination of all those variables, and it goes into z. And the z, what I'm trying to do is y is equal to f of z. Okay, it's a function of z. Okay, it's not a function of x, where z is a function of x, but y is a function of z, where z is 1 by 1 plus e to the power minus z in this term. Okay, and this maps any real value numbers in the range of 0 to 1. So the threshold is between 0 to 1, and this is 0.5. So for me, what should be the cost function of the logistic regression? So the cost function of a logistic regression is called as a log loss or the binary cross entropy. Okay, which in other words is the this way that I'm trying to minimize the value, so that when it is, suppose say y, where y is the actual value and y cap is the predicted value. Okay, so what I'm trying to do, in other words, I can write this as y cap to the power y, right, into 1 minus y cap to the power 1 minus y, okay, where y is the actual value and y cap is my target value. So my objective is to this, like whenever say my target value is 0, so 0 to the power, so actually 0, right? So anything to the power 0 is what? 1. It is y cap into 1 minus y cap to the power 1. Okay, so y cap minus, so this is my, in the case of 0. In case of 1, this would be y cap into 1 minus y cap. So every time in case of say it is either 0 or 1, it would always follow the same cost function. Okay, and I'm taking a log out of it so that it converges faster. So this is also a convex function. So if you remember convex and the concave function, so convex function is something like this, where my assumption is that there is a local or a global minima for my cost function, and it converges over there. And I'm taking a log out of it, and log is also a convex in it. So log of a convex function is also a convex function. And this is my cost function that I have. So in my cost function, this is, if you see, for I'm taking a mean out of it, right? For the loss function that I have, I'm taking a sum of it and taking a mean out of it. My assumption is that if I take minimize this cost function, then I'll be able to find that particular beta, right? Particular z, or the z can ultimately find my particular beta, so that my model gives me the best output, which would be a good classifier between the zeros and the ones. Okay. And the parameter estimation of, in the case of logistic regression, also follows the same, the gradient descent what we have. So beta j is equal to beta j minus alpha of this differentiation of this particular loss function or the cost function. Okay. Let's see an example of how we can do the same in Python. Okay. In that case, my target was on the continuous variable. Over here, my target is on the categorical variable. So here I have made another data set where this is the number of hours studied, the attendance of a particular students, the number of assignment completed, gender. In that case, it was the exam score, and over here it is the pass, whether the particular student is passing or failing. Okay, my target is this. Similarly, my model is not able to understand any of the categorical variables. So what I will do is one hot encode. I have done the one hot encoding using pandas.getDummies, and I'm trying to fit the logistic regression on top of it. So I have fitted my logistic regression, and I have done the train test split, like 20% of the data is in testing, 80% is in training. And how many samples have I taken? So there are 100 samples. Okay. So out of 100 samples in training, there would be 80. In testing, there would be what? 20. And here there are the, yeah, sorry.
Sir, like you wrote np dot sample series equals brackets and you wrote 42. Like, what is the meaning of that?
Yeah, so this like you can omit it. So because I am doing generating samples on the go to maintain uniformity, that the same sample, same number of samples which I'm generating. That means suppose say for the number of past students, what I have made is out of 100 samples, suppose I have made 60 and 40, right? 60 students have passed and 40 students have failed, right? To maintain uniformity that the same 60 and 40 should be there, I'm trying to fix a particular numbers. So the random number generator which my system has, it should always be predicting the fixed set of numbers so that my overall target that I'm trying to make is always correct. Okay. See the hour study, this is what I have, like randomly I have generated those numbers. Okay. These all numbers need to be constant every time I'm trying to iterate through it. Each time I run, the numbers need to be the same. That is why I have fixed this number. So it can be 42, it can be 112, anything which I can fix that. So, but I need to keep in mind that the same number need to be given every time.
Means you're saying that you need to get that many number of items, like 42.
No, see the hour studied, right? Here 3.74 is coming, 9.5 is coming, right? So every time I do that, it needs to follow in such a way so that 3.74, 3.14, this all combinations need to be followed every time. Okay. Let me change this number. In place of 42, let me make it 45. Okay. If I make it 45, can you see, right? The number have got changed. Hello.
Yes, sir. Yes, sir.
Okay. So if I make it back to 42, the number again, it goes back to the same. How I had predicted, how I had made those data set. Got it, right?
Yes, sir, got it.
Yeah. So I have created those dummy variables, fitted, like made those 10 to split. And in my testing, so 80 number of samples were in my training, right? And 20 number of samples were in my testing. So out of 20 samples, 14 students have, let me give you the overview from the training also. So out of the 80 samples, right? 48 samples I have for which the target is 0, means 48 students have failed and 32 students have passed. Okay. That means there is a good proportion between the uh, people who have passed versus people who have failed. Similarly, I can do that for the test as well. So for test, there is 14 and 6. So the way I have done the split is random split. Okay. What I can also do is I can do a stratify split. And if I do the stratify split, what it will do is it will try to maintain that particular number, the suppose say the number of people who have passed or failed is say 60 is to 40, then that 60 to 40 ratio would be followed in the training data set and also in the testing data set. Okay, hope that is clear to all. And after I have fit that particular model, so using scikit-learn, I have taken this logistic regression, and after I have fit the particular model, these are the values which I am getting. Okay, more on this will be coming and covering like what are the various matrices for the uh, logistic regression and how to quantify and say that how my if my model is good or not. Okay. So for linear regression, if you remember, we had done the hypothesis test to signify like which of the variables are important to me or not, right? So in this case, we can do the similar kind of an exercise, which is the Waltz test. Okay. So if anyone can make me recall, like for continuous variables, what were the test we were doing? Like Z test, T test, right? Can anybody say me like for categorical variables, what are the different tests we had covered?
We can cover chi-square test.
Yeah, exactly. So chi-square test is used for the categorical variables, just to find out the goodness of fit test, right? And test for independence for categorical variables. So given that my target is categorical, okay, my target is categorical, whether the people have passed or not passed, right? Based on this categories, I want to test that whether my samples which I am taking, the features which I am taking, whether those are statistically significant or not for my model. Okay. So for that, what we can do is the Wald test. Okay. So Wald test is nothing but it tries to find out the statistical significance of a particular feature. So in Wald's test, if I get my particular p-value, if it is more than 0.05, then I consider that to be as a statistically significant feature for my particular model. Okay. So if I run this, then I see that it has done a chi-square test, and the constant value is less than 0.05 and attendance is less than 0.05, right? So here also what I can say that attendance and the constant are playing a crucial role for my model to be using these two features only I can build a particular model and it can predict my uh, output like in a statistically significant way. If none of these are coming as statistically significant, then I have to change my model and I have to use any other models. Okay. Any doubts in logistic regression? I think we have like covered that in a hurry. I think more of those on the derivation and all those things we'll be getting that in the material which the uh, people from the FEBS would be providing back to you. You can go through those. You can get to know like how to do the derivation, how to find out the particular parameter estimation using gradient descent. Okay. More on this, like you will be like that will be covered in the materials which you will be getting. Any doubts till now? Okay. So coming back to the next topic is the polynomial regression. So in logistic regression, what we have, sorry, in linear regression, what we have considered is there is a linear relationship between the target and the predicted. Okay. That means as x increases, y is also increasing. If x decreases, y is also decreasing, right? But sorry, this is not like is decreasing. If x is increasing, y is increasing. If x is decreasing, y is also decreasing. This is the linear relationship between the y and the x. Okay. Suppose if there is a non-linear relationship between the y and the x. Okay. That means if there is a square kind of a this thing or this kind of a relationship. Okay. So how to model that using linear regression? So to tackle around that, there's something called as a polynomial regression. So this is how a simple linear regression would do, but it would not generalize well for a non-linear relationship if it is there between the x and the y. Okay, it would try to predict this line, but the differences what you would see is quite huge, and the model would not generalize for that. So to tackle around that, what we can do is, if I create other features which is polynomial in nature, given that this, I assume that this is a following a square graph, right? When x is 1, y is 1, x is 2, y is 4, like a square relation. Okay, y is equal to x square. If I know it follows this relation, then I can do this polynomial model on top of it. Okay, and it would not fit a line, it would fit a this kind of a curved graph, which would be saying about the particular model and generalizing well to the unknown coefficients. Okay, so this is the equation for the polynomial regression, where beta is y is beta naught plus beta 1x plus beta 2x square. Given that I have no idea as what kind of relationship is there between y and x, what I can do is I can create multiple polynomial features out of it, multiple quadratic features out of it. One can be x square, one can be x to x cube, xn, and all those things, so that I'll leave it to the model to understand that. And from the statistical test, I can see that whether these features are coming as important to me or not. And based on that, I can use those corresponding features back into my model. So similarly, how you can do the same in Python is under same the sklearn, there is something called as the, I have used the same linear regression, but what I am trying to do is I'm trying to use the polynomial features. Okay, for the same thing, for the same x and the y split, I am trying to create polynomial features. So this is a degree of 2. Okay, I am creating x square terms. Okay, so it would be for every feature that I have, like our studied attendance and assignment completed, for each of this, I am creating another term, which is like our study square, attendance square, assignment completed square. Okay, like x equal to 1 hour studied, and the other is the cross features also, like hour studied into attendance, attendance into assignment completed. These all features is also I am taking into consideration, like x plus y whole square, x square plus y square plus 2xy, that kind of a relationship I am trying to build over here. And these are the features that I have done. So suppose, say, if you look into the original xtrain, so this was my xtrain that I had. Okay, after doing the polynomial features, so this would how my xtrain would be, xtrain poly. Earlier there were how many features? Only 3 features, but here there are 1 2 3 4 5 6 7 8 9 10 10. Okay, the reason being I have made other dependent features also, like hour square, attendance square, assignment square, and the also the hours studied into attendance, this into this into this, right? Assignment completed into attendance, attendance into hours studied, all those things. So this would make that into the other extra features, and using those features, so if I make this as 3, so the number of features would also improve exponentially. Okay, so the number of features are also increasing. If I make it 1, it would be the same as it was before. Okay, like 4 features are there. So using the linear regression, what I'm trying to do is I'm trying to use the polynomial features and the same target variable which was previously there, and then make the prediction. So after making the prediction, this is like for the exam score, this is the plane what I'm getting, and this is the scatter plot out of it. And if I okay, so this is the same thing. The other thing is, what is important is the bias variance. Yeah.
Sir, so basically in polynomial regression, we are making new features and then just applying linear regression, correct?
Yeah. The model would be the
But
same.
so
Yeah.
but the assumptions for the linear regression was that the features should not be like multicollinearity should not be there.
Yeah.
So wouldn't one of the assumption be violated as the, like if we take a feature x and the feature x square, so they might be
Mhm.
related, correlated, right?
Yeah, yeah, that is true. So that would be correlated, but when I'm trying to, if I try to build a basic model out of it, then that would be violated and that would be coming up in my assumption also. So in that case, a linear regression would not be the best if I have a nonlinear relationship within my data. If I don't have any other modeling techniques, I have to only go with linear regression, then that is the only way how I can use the non-linear features within my data. So in that case, the other statistical test, if I will do, like the a t-test, if I will do, it will say that the particular feature is not adding any significance into my output. It will be like dropping out of it.
Okay.
Mm.
Okay, so we need to first check if polynomial regression can be applied or not, right?
Yeah. First, see if there is a nonlinear relationship within the data, then it's better to avoid the linear regression. But in the worst case, if I don't have any other modeling technique, then we need to go with the linear regression using the polynomial features.
Okay. Okay,
Yeah.
sir.
So coming to the other thing of the bias variance trade-off, okay? So the bias variance trade-off is the plot of the model complexity versus the error. Okay. Model complexity, I mean, is how complex is my model. In terms of complexity is how much complex or how many input parameters are there for my model. So if I write for a linear regression, so y is equal to beta x plus c, right? So my parameters for linear regression are two. One is beta, the other is the C. So these two are the parameters which I am using for building my model. As I go more deep and deep, as I like build some of the complex models, then the number of parameters increases exponentially. Okay. And that makes the model much more complex and much more prone to overfitting, given that I am trying to much more generalize, not generalize my data, much more constrict my data. Suppose there are multiple parameters. Suppose in the case of a, which we will cover later, like in the case of a random forest and all those things, which are much more complex models, which take a lot of time, all those things, there the features become much more, the parameters become much more prone to overfitting. So what as a data professional we need to have is we need to trade off between the bias and the variance. So high bias means the model has underfitted. That means if I use a normal simple model, right? Suppose I have got the data points, right? 1, 2, 3, 4, right? I know that the next would be a linear output, like the next output would be the 5. So if I use a simple model like this, which just predicts the output and based on the past data points which I had seen. So if I use a simple model, then it would be underfitting into my data. That means it is not quite generalizing into the data, it is underfitting into my data. Suppose say the output was 15 in place of 5, then my model has not fitted, it has fitted into this thing. So it is not quite generalistic. So if I use a complex model, then the bias should have been low. So my target should be how my bias should be low and my variance should be low. So variance is how much variance is there within the particular output. That means how generalized my model is. If my variance is high, then it is an overfit model. If my bias is high, then it is an overfit model. So always remember that it is something BUVO, high bias, then it is an underfit, high variance, then it is an overfit. Just remember this thing. It is mostly asked in many of the interviews and many of the companies they ask like how to solve for this bias, how to solve for this variance. So in that case, like most of the things, like you might be not sure, like if my bias is high, with will that be underfit or will that be overfit? So to remember around that, keep this term in mind. It needs to be, it is always, it is like mostly BUVO. If it is high bias, then it is underfit. If it is high variance, it is under overfit. And my target is to make a trade-off between both of that so that my bias is low and my variance is also low. So overfit, like how can we solve for overfitting? Like one of the most common method of solving for overfitting is like if I can not to use two complex models, right? Then my overfitting problem can be solved. But that would not solve for my total use case as a whole. Suppose say like the case of a polynomial regression we had seen, right? Even if you are using a simple model for a polynomial regression, but still the model features would be highly correlated to each other, and that would be not using giving me the best output. So then the some of the remedies are like using simpler models, regularization, right? Regularization parameters, like L1 regulation, L2 regulation, which we had seen, doing cross validation, like splitting up data into multiple chunks so that I can cross validate and test my data and multiple unseen data, and doing feature selection. Okay. And the other way is also like to use more data. If my model is underfit, what I can do? Then I can use some complex models. Okay, the opposite of overfitting, and add more features. Here I was trying to decrease the features. Here I am adding to increase the features. Here I was trying to use more data. Here I will try to decrease the data. Okay, and tune the hyperparameter and the feature engineering. So these are the things how you can solve for the overfitting and the underfitting thing. Mostly what we do is we go for regularization, we go for cross validation, because data, getting more data can be complicated thing. We are not sure like getting more data would be beneficial for us or not, if we can get the right amount of data or not. And to tackle for underfitting, what we do is we do the hyperparameter tuning and do some feature engineering on top of it. Okay, so these are the common techniques that we follow to have the bias variance trade-off. Coming to the other thing of advanced supervised algorithms, one is the support vector machines. Has anybody got any doubt on the bias variance trade-off or the overfitting underfitting thing?
No, sir. I think so. We can proceed.
Okay. So the other thing what we have like in some of the advanced supervised learnings are what we will cover in today's session is the SVM and the naive Bayes. Okay. So SVM is also a supervised learning in which it can be used for both. Okay. So if you remember for linear regression, what we had done, it was used only for regression task, and logistic regression was used only for classification task. Okay. But SVM is such a model which can be used for both classification and regression, both. That means it can predict, it can be either 0 or 1, or it can give a continuous variable that it can be 0, 1, 2, 3, all those things. And these are particularly effective in high dimensional spaces, right? And are widely used for classification tasks. Though it can be used for regression, but mostly it is used for classification task, more on which we'll be discussing now. So suppose say this is what is my x and this is what is my in place of x2, you can also keep it as y. Okay. So suppose if this belongs to one class and this belongs to other class, the blue boxes belongs to one class and green dots belong to the other classes. Okay. I am trying to find a plane which can separate my two classes effectively. Okay. To find this plane, what should be my objective? Such that the distance between this point, this last green dot, and the plane needs to be the highest, right? And similarly, the blue dot and the last blue dot and my plane needs to be highest. Okay. My overall objective is to find this plane so that the distance between this green dot to this plane and this blue box to this plane is the highest. Okay. So this is for a 2D axis. If I have got a multiple number of axes, then I can use a plane. Okay, so plane is used interchangeably. So this is a line for this case, but we are saying that is a hyperplane. And similarly, a hyperplane can also be built for multiple axes. If the data is represented in multiple axes, then we can go ahead and use it for those cases. So my objective is how I can find this particular plane so that my distance is maximized. And this is called as the positive hyperplane, and this is called as the negative hyperplane. Okay. This much difference what we are getting is known as the support. Okay. So this support what we are getting gives the name of the support vector machines. This support needs to be high. So anything which is coming more than that, I will classify that as a 1 because it's in the positive hyperplane. Anything which is coming less than the support is considered as negative hyperplane, which I can take it as 0. Okay. So this was for two class classification, right? If I have got two classes, I can build this kind of a model, build this kind of a plane, and I can do that. Suppose say I have got multiple classes. Okay, there is another class over here, right? That then how can I build a model which can also distribute, like find the classes between this and this and this and this. So for that, I can go for multi-class classification. Okay, so there are different strategies how we can build a multi-class classification. One is the one versus rest strategy. The other is the one versus one strategy. In one versus rest strategy, what I am trying to do is I'm trying to build one classifier per class. That means the number of classifiers, number of classes that I have, so many classifiers I will be building. And during prediction, the classifier with the highest confidence score determines the class label. Okay. And in one versus one, what I'm trying to do is n into n minus 1 by 2 number of classifiers I'm trying to build. Suppose there are three, then what I will do 3 into 2, 6 by 2. So three classes, three binary classifiers that will try to build. Okay. And during prediction, what I will try to do is a voting mechanism. That means I will try to take an aggregate out of all those classifiers and say that this belongs to this particular class or not. Okay, so this is an example of how I can build for a multi-class classification. So this is the one versus rest strategy where I am for this class, I am trying to build the number of classifiers should be 3. Okay, because there are 3 classes. So blue versus green and red, green versus this, and this versus this. So there would be 3 classifiers, and given an unseen data, it would be fed into both all of these 3, and it would give me an output, like what is the output of that in each of the cases. But in one versus one, what I will do is I will omit the other class and just try to build a hyperplane, assuming that is a normal SVM. Okay. And based on the aggregated value, I will say that whether that belongs to a particular class, class 1 or class 2. But the thing is, if I have got like nonlinear data within the for my SVM, suppose say this is my uh, model which I'm trying to build, but there are nonlinear data with nonlinear data in my case. So how to handle those nonlinear data? So to handle those nonlinear data, what we do is the kernel trick. Okay, like there are different kind of kernels which one can go with. So one is the linear kernel where we don't do anything, we just use the same as it is, and the other is the polynomial kernel. In this, as in the case of polynomial regression, what you have seen, we are trying to make the polynomial features out of it, like x square, x cube, x to the power 4, all those things, and then try to build a hyperplane on top of it. And the other is the radial basis function. So radial basis function is nothing but it is trying to find the Euclidean distance between the two data points. And based on that, we are trying to minimize those Euclidean distance between the data points and find a hyperplane which can be better suitable for my classification task. Okay, let's see how this radial basis function is done. So suppose these are two data points, 1, 2, and 2, 3. Okay, first I'm trying to find the Euclidean distance. Euclidean distance is what? X2 minus x1 whole square plus y2 minus y1 whole square. Okay, we have got it root 2. And assuming a gamma of 0.5, we are trying to find the kernel value for this. So using the radial basis function, I found out like 0.3679 is the value for these two data points. That means I'm saying that these two data points are in the, say, a large dimension space. These are 0.3679 distance apart as compared to each other. So using these all values, what I can do is I can go back to my SVM and build a model on top of it, so that the number of dimension has increased, given that on the whole of the data points that I have decreased my dimension and also the non-linearity. Suppose this was following a non-linear distribution. This was also following non-linear distribution. What I can do is I can convert that into a sort of a linear dimension in the larger space. And this is how you can do the same in, suppose I have the same data set, and using the sklearn library, I can fit a classifier on top of it, and this would give me the output. Okay, using the sklearn, in the sklearn there is SVM and there is SVC. SVC is a support vector classifier, and similarly I can go for, if I do for regression, then SVR, support vector regression. And the other is the last for today is the naive Bayes classifier, or the naive Bayes technique. So naive Bayes is a probabilistic algorithm based on the Bayes theorem. So I think all of you might be quite acquainted with the Bayes theorem, wherein we are saying that P of C given X, where C is the class and X is the variable, is equivalent to P of X given C, right? Where P of X given C is the likelihood of the features X given class C into PC, where PC is the probability of the occurrence of the class C. It is the prior probability of the occurrence of class C. And P of X is the marginal likelihood of the feature X. Okay. Suppose these are the features that I have, right? So these are the X's and these are the uh, Y. Okay. And Y is my, so 1, 0, 1. And these are the other features that I have. So based on the posterior probability of the occurrence of the Y's and the X's and the priors, I can model an algorithm so that it can say that whether the particular feature belongs to a class X, class 1 or 0. Okay. And the naive part of the naive Bayes comes from the assumption that the features in the dataset are independent of each other. Okay. As in the case of linear regression, we had seen, right? The residuals are independent of each other. Similarly, here also what the assumption is, all the feature values are independent of each other. That is the one of the common assumption what we follow in the case of naive Bayes. Though that is not true in the overall scenario, global scenario, but that is what we generally follow over here. So there are different kind of naive Bayes techniques which are there. One is the Gaussian naive Bayes, the multinomial naive Bayes, and the Bernoulli naive Bayes. So these are the corresponding formulas for this. So these are the corresponding formulas for this, and mostly people go with the multinomial naive Bayes, given that here, if you see, the NIC is the count of the index of the feature Xi in class C, and NC is the total count of the features in class C. Okay, and alpha is the smoothing parameter. So this is mostly used in the case of text classification. Suppose you have got a text and you want to say that whether that is a spam or not, right? So in those cases, multinomial naive Bayes is mostly used, given that it takes the frequency of the occurrence of the particular word. Suppose there is a word like good. Good is a like a positive word, and bad is a negative word. So number of occurrence of the words in the particular class, we take those into consideration and build the multinomial naive Bayes. And the other is the Bernoulli naive Bayes, like where we assume that there is a Bernoulli distribution between the classes. Let's see how that can be built over here. So similarly in scikit-learn, there is a naive Bayes, and suppose we are going ahead with the Gaussian naive Bayes. Okay. So that is how you can, on the same data set what we had for the pass and the fail, we can use the Gaussian naive Bayes, and that is how it builds the model and gives a accuracy of 85%. Okay, here it is giving an accuracy of 90%. So to evaluate any of the model, suppose I have built all those model and done a training on top of it, and I am saying that this is the best model that I have got, right? So how to say that which is the best model which is there? So there are different evaluation matrices, or it can also be said as metrics. Okay, so it can be used interchangeably. The plural form of metric is metrics and also matrices. Okay, so for regression there are different evaluation matrices, and for classification there are different evaluation matrices. So for regression, what we mostly go around with is the mean absolute error, which is the absolute difference between the target and the actual value. Okay. For n number of samples that I have, I am just taking a absolute difference between the predicted minus actual, and then taking a mean out of it or average out of it. The other is the mean squared error, wherein in place of an absolute loss, I am taking the squared error out of it. So the thing is, if I uh, go with the mean absolute error, it gives an idea of how wrong the predictions are on an average. Okay. But in the mean squared error, if you remember in the case of linear regression, we had seen, right? For cases like where there is a large outlier within the data, in that case, our error value would also be highest. And in that case, it penalizes large errors more than the MAE. In MAE, it was not giving that much importance to the large error. Suppose say the error was 100. Okay, in mean absolute error, the error value would also be 100. But in mean squared error, as we are taking a square term out of it, so it would be what? 10,000. Okay. This is the power of what we get with the using of the mean squared error. So we will be trying to minimize the error more. And the other is the root mean square error. So given that in mean square error, we are taking a square term out of it, so it was not in the correct units of measurement as in my base data was. So to have the correct units of measurement or in the same units of measurement, what we have to do is we can take a square out of it. So after taking the mean value of this, we can take the square of this, and that would give me the root of the mean square error. So although it targets for the large errors, and also it can be in the same scale as the target variable. So it serves the dual purpose for my task. And for any of the goodness of the fit of my model, what we look into is the R square value. Okay. R square and the adjusted R square. So what we have covered right now is the R square. So R square is nothing but the 1 minus the, this is what? The sum of squared error. Okay. This is the sum of squared error. And this is the, what is Y? Y is my actuals, and Y bar is the average of all the samples which I had taken. So this is the total sum of error. Sorry, this is the total sum squared, not error, because here we are not targeting over here. So for all the samples that I have, so how much variance is? So if I take a difference of my mean value versus the actuals value, I can, this would be, in other words, be the variance for my data. Okay. So how much variance is there within my target value, and how much error is coming up within the targeted values and my predicted values. So if I take a ratio of that and subtract that with 1, that gives me the R square. Okay. So R square value would always be between 0 to 1, where 1 indicates that it is near to perfect prediction and 0 indicates that the model fails to predict the target value. Okay. And adjusted square is also another term where when we look into, like, if we add more features into my model, is that going to increase my more features and more data points into my model, is that going to increase my error term statistically or not? Let's see an example of how this can be done in Python. Suppose this is my actual values, right? 10, 20, 30, 40, 50. And these are my predicted values, 12, 18. These are my predicted values. Okay. If I calculate the mean absolute value, so how much was the difference? So this was 2, this was something 2, right? Everywhere it was 2 only. So mean absolute error was coming as 2. So mean squared error, given that it is a squared loss, so it is coming as 4. If I take a square root of the mean square error, it is coming as 2. So mean absolute error and mean square error both are the same. And R square error, if I look at, it would be coming as 0.98. That means we are saying that the predicted value is good as compared to the actual value. So just by deviating by plus or minus 2, our model is good. And for classification, if I would see, in the case of regression, what we were trying to do is we were trying to predict between y minus y cap. That means the absolute or the square differences between the value that is trying to predict. We were trying to minimize this thing. Suppose it is 1 and it is 1.1. Okay. We were trying to find the difference, that is 0.1 is what is my difference. I'm trying to minimize this. Whereas in case of a classification, we are not trying to find out what is the absolute difference between say 1 and 1.1, because both of this would be anyway be 1, because our target is either true or false. Okay, our target should be like how many classes are correctly classified as true negative, how many instances are correctly classified as true positive. So this is the confusion matrix what we have. So confusion matrix is mostly used for classification thing. So in this matrix, we are trying to plot the, not plot, we are trying to write down how many true negative are being classified by the model, how many true positive have been classified by the model, how many instances have been falsely classified as negative. If you remember the type 1 error and the type 2 error, which we had discussed in the case of the uh, um, hypothesis testing. So in that case, we were trying to minimize the type 1 error. Okay. So this is the same thing, the confusion matrix, where we are trying to maximize the true negative and true positive and try to minimize the false positive and the false negative. Okay. Suppose our target value is 1 and we are trying to predict, we have predicted that as 0. Okay. So this is what, a true positive or a true negative, or false positive or false negative. Can anybody say me? This was my actual and this is what I have predicted. This is true positive or true negative, or false positive or false negative. Hello.
Yes, sir, your voice is clear.
Yeah, can anybody say me, like whoever has been following me? My actual need to be 1. Suppose I want to say that this is orange, but someone is saying that this is not orange. We
False
have,
negative.
yeah, it is falsely negative. Okay, false negative. It would go and fall within this. If it would had been 0 and we had predicted that as 1, so we are what? Falsely, we are seeing that as a positive. Okay. Falsely saying it as a positive is false positive, and falsely saying it as negative is false negative. Just remember this thing. This is mostly helpful for you and mostly used for solving any of the use cases what you have got in say of classification and all those things. So if it is truly positive, that means it is actually it is 1 and we are predicting that as 1. So it is true positive. And if it is actually 0 and we are predicting that as 0, so it is true negative. That means truly negative the model has predicted and truly positive the model has predicted. So accuracy is the measure of the overall correctness of the model. That means it is the ratio of the true positive plus true negative by all the absolute other terms. That is the accuracy. So generally we want our accuracy to be high. And precision is nothing but the ratio of the true positive to the true positive plus false positive. So true positive plus false positive, what it would give? This would give me this term. Okay. So true positive plus false positive gives us the how many terms our model has predicted as positive. Okay. Just remember how many terms the model has predicted as positive. Out of that, how many in actual are positive. So that would give me the predictability power of my model. Okay. The other thing is the recall. So recall is the true positive plus false negative, this and this. So out of the things which are, suppose this is 1, this is 0, this is 1, this is 0. Okay. Out of the ones which are actually true, which have, like, these are the actuals and these are the predicted. Out of the ones which are actually true, how much of those we are predicting those as positive, that is recall. Out of those which have been predicted by model as positive, and out of that which are actually true, that is the precision. Okay, so that is the difference between the recall and the precision. So it depends upon the use case. We can have either recall to be recall to be more, or the precision to be less, or we want both to be high. Okay, so in that case, we where we want to have the trade-off between the precision and the recall, where what we do is we take the F1 score, or this can be F beta score also, based on the weightage that we want to give to the precision and recall. So as we are keeping both equally, so it is 2 into twice into precision recall by precision plus recall, or otherwise it is 1 plus beta into precision into recall by beta times of precision plus 1 minus beta times of the recall. Okay. The other thing is the ROC curve and the AOC. Okay, so ROC curve is the ratio, is the plot between the true positive rate to the false positive rate, wherein true positive rate is the recall. That means it says that what is the predictability power of my model. That means how much is my model trying to predict truly out of all the true samples that I have. Okay, and false positive rate is the how much is my model trying to falsely say data are positive. So the how much, if I do the other way around, like false positive by false positive plus true positive, that will give it the false positive rate. That means how much is my model saying data as falsely as compared to the predictability of my model. So the ratio of the true positive rate and the false positive rate, if I try to build a model for different thresholds that I have, that would give me the ROC curve. So my objective is to maximize the area under the ROC curve. That means this is my perfect this thing. That means my true positive rate would be 1 and my false positive rate would be 0. Okay. This is my ideal condition. So any curve which follows this thing, like the more of this, because this is a random classifier, any one can say, or any thing which is say 0.5, like a coin toss would also say that whether thing would be positive or negative. So the probability of occurrence is 0.5. So anything which is more than this, my target is to have a curve so that the area under the curve is maximum. Okay, so the AOC ROC curve is generally what we follow for classification, and the area under the curve needs to be the highest for a model to be perfect. Okay, let's see some example of how we can implement the same. Suppose these are the actual labels and these are the predicted labels for my model. Okay, let's calculate the accuracy. So using sklearn matrices, metrics, there are accuracy score, precision, recall, F1 score, and confusion metrics. So over here, like from this, you can see, right, there are true positive, true negative, true positive, false negative. Okay, and based on that, we are calculating the accuracy, precision, recall, F1 score, and all those things. Suppose say these are the actuals, and I have changed the value to be something like this. Based on that, my accuracy is changing, precision is changing, and all those things are changing. So accuracy is 50% right now, so which is quite bad. That means my model is not quite good. So anything more than 50% and the precision and the recall value accordingly would give me an intuition as how good my model is. Okay. I think, yeah, that's all for today. Has anybody got any question? I know, like, we have covered a lot of topics within a short amount of time. Hello.
If anyone have any doubt, they can raise their hand and then ask their doubts.
I will be passing on the slides and also the passing on the uh, notebook that I have created. You can go through them and further get a clarity on that. I would strictly ask you to revise through that so that if there are any doubt, you can come back and ask again. Anyone has got any doubt? Okay, I hope it is a no. Yeah, Aditya.
Sir, I think no one has any doubt. So thank you for the session, sir.
Yeah. So let's plan to meet tomorrow. Tomorrow we'll be covering some other algorithms, some other more advanced stuffs from machine learning, wherein we'll be looking into decision trees, random forest, bagging, boosting, hyperparameter tuning, all those stuffs. So brush all these concepts today because those are also going to be helpful tomorrow.
Yes, sir. So thank you, sir, for the session. And I hope to see you all tomorrow. Thank you, everyone.
Thank you all. Bye.
Thank you, sir.